Use what you have. Learn on one. Invite learning in.
Yes, we're recording. Okay, we have to have a look at the next unit, Unit 4. And the unit is about the basic units that we use when we measure things, all right? We talk about a system international for units over here. SI units, System International. It's a set of units that was decided at a convention that is accepted internationally as the basic unit from which, when you do measurements, so that if you sit in one country and you're doing an experiment and somebody else in another country does an experiment and you want to compare your results, then it is done in the same unit, because if I worked in kilometers per hour and they work with in another country at miles per hour, it's going to be very difficult to sit and compare. No, you would have to convert them. So we have a system international for basic units. Now, most of the units you know, we've worked with them. Length, all right, is done in meters. The symbol for meter is a small letter M. We've measured lengths grade 5, 6, 7 already, no? Okay, so length is no problem. The basic unit is meter, but it doesn't mean we can't work with millimeters or centimeters. We will see over here, we go and have a look at derived units, and then you will see that the other units are taken from the basic unit, all right? And then we have a metric system according to which we adjust them. Okay, so the unit for time is in seconds. A very common error. You don't write SEC. That's short for secondary, not seconds. No. So take note, time is measured in seconds. The symbol for time in seconds is a small letter S. All right. Electric current. Now you've done a little bit of electricity. The unit, the ampere, in which we measure current, is also an SI unit. Then mass. Mass, the SI unit is in kilogram. And actually, you've been working with it without thinking about it. Remember in grade 8, I would have said to you that if you want to convert your mass to weight, we multiply mass in kilogram. No. Times 10. And why did we use kilogram? It's the SI unit, the international unit. No. Okay, so mass in kilogram. The unit for kilogram is a small letter K and a small letter G, not a capital letter K. That means something different. Then when we get to chemistry, we will have a look at the amount of a substance. That's number of moles. Now, I won't worry too much about it. When we do the work, I'll explain to you a little bit more about the mole. But a mole is similar to a dozen. If I say to you, I have a dozen children, how many children do I have? 12. Okay. If I have 1 mole of something, I have got 6.02 times 10 to the power 27 of them. Okay. So a mole is just a quantity, it's just a very large quantity. Okay, we'll come back to mole when we do that specific part. Then temperature, even though we work with degrees Celsius is not the SI unit for temperature. It is actually something known as the Kelvin. Okay? And the Kelvin then is a temperature scale that is related to the energy of the particles at absolute zero. Okay, I'll do it then. Okay, so temperature is with Kelvin. So temperature is something called the Kelvin. The symbol for a Kelvin is just a capital letter K. It's not complicated. I'll come back to Kelvin in a moment. And then luminous intensity, the amount of light given off by a candle or by a bulb or by a fire, is known as candela CD. Okay. We don't really work much with luminous intensity. If I remember correctly, there isn't a calculation containing this one, but we do work with the others. So take note, but I don't think it's all that important. All right. Now, once we've got the 7 basic SI units, meters, seconds, ampere, kilograms, moles, Kelvin, and candela, from that, we can derive other units. If I measure a length of a line, I measure from the one end to the other end, and I have, for example, 0.14 meters. That's a length. Meters, then, is the SI unit for distance. So when I go and work out an area, I need another measurement, which is also a length. All right, so let's say I have this surface and I want to work out that area. Let's say the length of that side is 0.15 meters. How do I work out the area? I multiply that side by that side, and that will give me the area. But now I am multiplying a meter by a meter, not so. And in algebra, if we multiply m times m, the answer is meters squared. So now square meters is not an SI unit, because the SI unit is just meters, but it's been derived. We use the meters to get to square meters. No? So we have a derived unit. It can be square meters, square decimeters, square centimeters, square millimeters. All right, those would be derived units. Then volume. When we want to work out the volume of an object, we need 3 measurements: a length times a breadth times a height, or a surface area times a length. Okay? Once again, we have 3 measurements. It's a meter times a meter times a meter times a meter, and that will give me cubic meters. So it's derived from a meter, but because we multiply a meter with a meter with a meter, we get a cubic meter, which then is a derived unit. So for volume, the derived units are cubic quantities: centimeters, cubic millimeters, cubic decimeters, etc. Then the calculation involving density. Now, we've not done this at this point, but you've done it previous years. Density is mass divided by volume. Now, mass has an SI unit. Volume is a derived unit. Okay? So the unit for density, if my mass was in kilogram and my volume was in meters cubed, now I go one step further. Now I've already got a derived unit in it, and my new unit is kilogram per cubic meter. It's also a derived unit from the original SI units. Do you understand? It's not difficult. Okay. So density is gram per cubic meter or kilogram per cubic meter, written like that. The format, kilogram per meter cubed, or kilogram, that means multiplied by a meter to the power minus 3. That minus 3 actually means 1 over the meter, ne? All right, so these two, that format and that format means exactly the same thing. Here, that slash over here means I'm dividing by cubic meters. That dot means I'm multiplying, but this means 1 over a meter cubed. So I'm actually multiplying by 1 over a cubic meter, which is equal to a kilogram divided by a meter, no? Okay. If we work with grams, generally the volume must be in cubic centimeters, so then we get the unit gram per cubic centimeter can be written either of those two ways. No. Energy, ability to do work. We did that, force, work and energy, no? Okay, so energy, when we look at the formula for work, because work done equals energy, it's force times distance. Okay? Force is mass in kilogram if it's a weight, times 10. So there's a derived unit. Okay? And distance is going to be meters. So if I multiply my newtons times my meter, a newton times a meter, we get the derived unit known as the joule. Be careful, it's not a newton per meter, it's a newton. Meter, newton times a meter. All right. Pressure. Can you remember the unit, the formula for pressure? Yes. Yeah? What is it? Force per unit area. So pressure is equal to force over area. Now we know that the newton is a derived unit and area is in meters squared. So the unit for pressure is derived from Newton per square meter, which we call a Pascal. No, we can write it like this. 1 Pascal is equal to 1 Newton per square meter. Yes, it's exactly the same. These are derived units. No. Then concentration of a solution. Now, when we did the basic units, we had a unit called the mole. I said to you it's a quantity. So it's the number of particles that you put in per cubic decimeter. It's derived. Decimeter is derived from a meter. There are 10 decimeters in a meter. Okay? There are 1,000 cubic decimeters in a cubic meter. All right. So it's derived eventually from, or originally from, meters. The unit then, mole per cubic decimeter, but we will come back to that unit when we do concentration calculations. Okay, in chemistry. Then, the next important thing that you must know of is prefixes that we work with. If I talk about a kilogram, what does it tell you? A kilogram or a kilometer? I've got 1,000 meters or 1,000 grams. No. So the prefix kilo implies we have got 10 to the power 3 of the basic unit. Okay. Less well-known ones, if you're into computers, you'll know what a terabyte is. A terabyte is a million. No, 12 zeros. 1 terabyte is a million bytes. Okay, lots of them. Yes, okay. But some of the terms aren't very well known. A picometer or a picogram is 10 to the power minus 12. And the symbol, if I want to write a picometer, the symbol for pico is a P. There. All right? Then we get nano. Now, nano is an easy one to remember because 9 also starts with an N. So nano is 10 to the power minus 9. All right. Then micro, a micrometer is 10 to the power minus 6. I would write Micro, that's the symbol. It's a U with a long line to start with. It's a Greek letter. A micrometer would imply I have a meter times 10 to the power minus 6. All right. So the moment you hear the word micro, you have to write 10 to the power minus 6. Okay. Of that specific unit. Then more well known is a millimeter. How many millimeters in a meter? 1,000. No. All right. Then a centimeter. It's all derived, yes. 100, all right, 10 to the power 2. Decimeter, 10 to the power minus 1. And then meter is just 1. No. Okay. Mega. If you've got megabucks, you've got $1,000,000. All right. 6 noughts, 10 to the power 6. Giga is 10 to the power 9. And a terabyte, computer boffins, 10 to the power 12. No, 10 to the power 12 will look like this. That's 10 to the power 12. No, 12 zeros. Yeah, lots of them. Okay, so those then are prefixes. Once again, when we get to them in specific examples, I'll refer back to it and we will remind you again of them. But eventually, some of them we work with quite a bit, some of them we don't work with all that often. All right, now, if we go and look at length, surface area, and volume, a length, very simply, if I have a line and I want to measure its length, I put my ruler down there on the 0 reading, and I lay my ruler down along that side. Let's say I want to know the length from A to B, then I will take the reading on my ruler. Okay, it's simply a measurement using an instrument taken from one point to another. All right. To get area, we need a surface. Your desk has a surface area, and we can figure out the area by taking the length and multiplying it with the breadth, and that should give you an area of a square or a rectangle. Now, it's a two-dimensional quantity because we use two values, a length and a breadth. This is going to be a one-dimensional quantity because we take one measurement. Okay. The area of a rectangle then, length times breadth. Slightly more difficult. The area of a triangle is going to be half of the base times the perpendicular height. So if the triangle looks something like that, let me just redraw that. Triangle, for example, looks something like that. Then that is the base. So it's half the base. And then you will take the perpendicular height. You would have to measure that value. So the area of a triangle is half times base times height. You can do it in any order because remember when you multiply, the order in which you multiply doesn't matter. You can take the whole base, multiply it with a whole height, and then you can halve it. It won't affect your answer. So the order of operation does not matter over here as long as you have half base times height. The area of a cylinder is pi r squared, or the area of a circle. There, here I have a circle. Remember, a line going through the center of that circle is the diameter, and the radius is half the diameter. Okay? So to get the area then of a circle, we have pi r squared. The unit will be in square meters if we worked with meters. Otherwise, if we work with centimeters or millimeters, it's square centimeters or square millimeters. That is area. Area is a two-dimensional quantity. Now, volume is a three-dimensional quantity because, very simply, if I have a milk carton. It's going to look something like that. Now I will need 3 sets of measurements. Okay? I will need the area of the base or the top, okay? And I will need the height. So we will need a length times a breadth times, well, actually, a height. It doesn't really matter. Let me just quickly do that over. Here's my carton, okay? We will need, for example, a height. Let me do in a different color. A height, that is going to be how high it stands, times a length, times a breadth. We need 3 quantities. Length times breadth times height. Or, how do I work out area? Area is length times breadth. And then I multiply the area with a height. I will also get a volume. Volume of a cylinder, the formula you must know, pi r squared times height, because the volume of a cylinder is the surface area of the cylinder, all right, multiplied by the height of that cylinder. No. All right, so volume of a cylinder, pi r squared times height. In what unit would we measure the volume of a cylinder? Meter cubed, not squared. Meter cubed, because volume is always centimeter cubed, meter cubed. Okay, it's a 3-dimensional unit. Now back to absolute zero and the Kelvin scale of temperature. This is very important. I said to you that the Kelvin is then one of our units that form a basic SI unit. But where does it come from? Back to the kinetic theory, the one you did in grade 8, that tells us particles, matter consists of particles. These particles have energy so they can move. What do we know about the movement of these particles? In gases, it's free. They can move a lot. In liquids, they also move fairly free, but it's slightly less than in gases. They don't just normally move out of the container on their own. All right? But if I pour it, it'll move to where I want it to go. So the particles can still move freely. We refer to the movement of particles in liquids and gases as diffusion. All right? In a solid, what do we know about the movement of particles? We said they vibrate about a fixed position. Okay. Now, the amount of movement particles have is also actually connected to the amount of energy particles have. If I have a gas and I put that gas into a fridge and I make the gas as cold as possible, the particles will not move a lot because they don't have a lot of energy. But if I took that same cylinder of gas and I put it outside in the sun or I threw it onto the fire, what's going to happen? That container is going to explode because the particles gain more energy and they can move more. Okay, now, the kinetic temperature scale has got to do with the energy of particles. And the theory behind it says, if I have matter and I start cooling it down, the movement of the particles will become less and less because the energy becomes less. If you have no energy, you can't move. Now, the theory about this temperature then is that at a temperature of 0 Kelvin, particles have no energy, so they cannot move. They can't even vibrate. Okay, that implies, for example, they can't exert a pressure. Do you understand? All right, and there's a whole theory about it. We will have a look at that when we do gas laws in terms of ideal gases and real gases. But the Kelvin temperature scale then is connected to the energy of the particles, and at 0 Kelvin, we refer to 0 Kelvin as the absolute zero. Okay? Now just have a look. If I have degrees Celsius, 0 degrees Celsius is the temperature at which water freezes. But do the water particles in the ice have no energy? No. So I can make ice colder and 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 colder until the particles have no energy. But would that be 0 degrees Celsius? Nope. 0 degrees Celsius is equivalent to 273.15 Kelvin. So if I go to minus 273.15 degrees Celsius, I will have 0. Fahrenheit is not a metric system. It's just a different way of measuring temperature. But once again, if you do a calculation, you can't use Celsius or Fahrenheit. You need to use Kelvin because it's connected to the energy. And we will use Kelvin when we do calculations involving gases and pressures and volumes. Okay. So then it's very important. They give you the temperature in degrees Celsius. You must convert it to Kelvin. Okay, now, so how do we convert to Kelvin? It's very simply, if I've got degrees Celsius, 0 degrees Celsius is equal to 273.15 Kelvin. So to go from Celsius to Kelvin, you plus 273.15. If you want to go from Kelvin to degrees Celsius, you simply minus that. Have a look. Let's say room temperature is 24 degrees Celsius. So what would the Kelvin temperature scale be? In Kelvin? So convert to Kelvin. What must we do? To go from degrees Celsius to Kelvin, we plus 273. Okay, so 24 plus 273.15 will give me 297.15 Kelvin. Do you follow? If I said to you, okay, today is a hot day, we have a temperature of 300 Kelvin, how many degrees Celsius would that be? You would go and take 300 minus 273.15. So the calculation is 300 minus 273.15 Kelvin, and that would give me, how much is that? 26.85 degrees Celsius. Do you follow? Yeah. So what is the value that you must remember? You must remember that to convert Kelvin to Celsius and Celsius to Kelvin, you add or subtract 273.15. Sometimes they will tell you very commonly to round it off to 273. Okay, we ignore the 0.15, but it depends on that. Okay, then there's an activity 16. I want you to do that. Have you done it? Good. We will mark it. Then standard and scientific notation is simply in the format 6.02, for example, times 10 to the power 23. A is an integer and N is an integer. Okay. Usually a unit and 2 decimal places. Then prefixes, we've had a look at the millimeters, decimeters, a terabyte or a terameter. Okay. Now there are some more prefixes and suffixes, and once again, as we get to them, we will have a look at them. If I say to you carbon monoxide, what do you know? Carbon bonded onto 1. Mono is 1. If I say carbon dioxide, carbon bonded onto 2 oxygens. So mono means 1, di means 2, tri means 3, tetra means 4, penta means 5, hexa is 6, hepta is 7, octa is 8, nonna is 9, deca is 10.